Okay, I see everybody is starting to arrive. We have about 1 minute left, so we'll just wait and see if some more people drop in. All right, so let's get started. Welcome to Plasma Session 2. We have some really nice speakers here. I don't want to eat into anyone's time, so let's get started. Our first keynote speaker is Michael Kedar. Michael Kedar is the A. James Clark Professor of Engineering at George Washington University. He's authored over 300 journal articles, 300 conference paper, and is the author of the textbook Plasma Engineering and Plasma Cancer Therapy. He received the Davidson Award in Plasma in Physics in 2017, the AIAA Engineer of the Award in 2016, was elected Fellow of the National Academy of Inventors, Fellow of the American Physical Society, Fellow of the American Institute of Astronautics and Aeronautics, is President of the Electric Rocket Propulsion Society, and has a continuing list, which I don't think we have time for. So without further ado, Michael, please begin your talk on adaptive plasmas for medical applications.
Thank you very much, Joyce. Thanks for inviting me. It's a pleasure to give a talk, and hopefully next time, as Ruben said earlier this morning, we meet in person. So I'm going to talk about adaptive plasmas, and it's nice to have actually first talk on plasma medicine, which is a relatively new field and emerging. And in the realm of plasma medicine, there are many aspects of it, many applications, I should say, of plasmas in various areas. So I'm going to focus on the last one, cancer therapy, but we will talk on very particular aspect of in this application. That application actually went quite far, and this is a clinical study. That's myself in the operation room. So we actually completed phase 1 recently, clinical trials using the cold plasmas. But now I would like to step back and discuss what plasma actually can do in the realm of cancer application. So there are two aspects of plasmas that usually people talking about. One is a chemical reactivities that plasma can produce. We're talking about atmospheric kind of plasma condition, and this reactivity can tailor particular pathways in cells. But recently, we also discovered that there is another modalities that simultaneously exist in the plasma, which we call physical effect for the lack of better name, and we will discuss that as well. So when we talk about chemical pathways and chemical reactivity, of course, holy grail of cancer application is selectivity. So this selectivity can be achieved through targeted delivery of reactive species to, say, cancer cells, right? And that can be done by taking into account that cancer cells naturally exhibit larger expression of particular channels called equiporins. Equiporins were discovered around early 2000. Nobel Prize was awarded for that discovery. But most cancer cells actually explore much larger expression of equiporins. And on the one hand, plasma actually can activate some of equiporins, as can show here, but also what some of the work show that really knocking down of some of this equiporin can actually turn off plasma effect. You can see we can restore cell viability if we turn this off. But really, to date, I believe that plasma was not really explored to full extent, and this is due to the fact that uniqueness of plasma in that particular application is due to the fact that plasma composition can actually be changed in real time on demand depending on specific requirement, of course, of target. So this is kind of instance of, say, treating normal tissue and cancer tissue and recording in real-time response, and that response can drive modification of some of the key discharge parameters that can change plasma reactivity. So this is how this adaptive platform can look like. So you have response that can be recorded, and then the modulation of, say, power, discharge, power, gas composition, and this is some example offline how this can be done. So, for example, this is a response of two different cell lines. This is a brain tumor, which is more resistive than, say, breast cancer cells. But by changing some of the plasma condition, we actually can get to the same outcome for these different cell lines. And this is another pair. And again, we can achieve the similar outcome. This is, of course, offline. Okay, now in addition, this is really two-way interaction. So plasma, it can be also affected in the presence of different cells. So here I show you, electron density measurement in the presence of different cells, the different cell lines, and you can see that there are some changes, noticeable changes, sufficient enough to be recorded. Or this is more of a temporal, resolution of those changes that the cells can impact on the plasma. Now, the system even can be self-adaptive in the sense that plasma can be shifted toward the cancer cell. So this is an example of experiment of what we call co-culture of, say, normal cells and cancer cell, and application of plasma jet right in the middle, and the shift of the plasma toward the cancer cell, right? So that's what we call self-adaptive. But now let's go back to a basic adaptive platform. So this is how it looks like. There is a air plasma source, can be in principle that creates some reactive oxygen nitrogen species. These species attack cells or in vivo some animals, and then the feedback in real time can be monitored that can lead to modification of applied condition, including voltages, gas composition, and duration. So here's some demonstration of how system looks like. And for initial recording on real time, we use what we call real-time glow assay that actually measure cell metabolism in real time continuously. So here's an example of this monitoring right from the treatment and in course of the treatment. And this is a kind of relative metabolic activity. Right away, we see that there is a stress that can be imposed. And of course, this stress later on can lead to decrease of cell viability and apoptosis, which is programmable cell death. So this is interesting that we can really distinguish between different treatment time in terms of seconds. Right, but more interested to that is that we actually can resolve also different discharge voltages. So as you can see, changes in discharge voltage can lead to different reaction of a cell that can be utilized for driving this adaptive platform. Now, there is another way to do it through electrical signal. So, for example, electrical impedance measurement of the system cell in the media, and the scanning can be done in certain range, and then we can monitor differences during the treatment. And what was interesting to discover that those changes in the impedance kind of linearly relate to cell viability. So therefore, instead of doing biological measurement, we can actually do this on the level of just the impedance. And this is a kind of result of autonomous system that say there is an overshoot of high enough voltage that will kill too many cells, or low voltage. If there is a goal that can be set, so then adaptive system can actually choose right condition, to achieve the goal. So let's talk a little bit about one of the important components of such adaptive system, which is a feedback control, right? So to that end, one can use model predictive control, which basically to say that we need to accumulate significant amount of experimental data that can lead to building a model, and then that model can be used to drive changes, right? While we are recording response in real time, right? And this is an example of treatment that, let's say we set a goal that we were going to do treatment every other day, and this is the goal. This is an ideal response in the red, and without any control, this would be a response that you achieve, which might be off from the target. And then with model predictive control, we actually at the end of the day can reach ideal response. Now, of course, this has a limitation, and the limitation are due to the fact that one needs to perform initial experiment to accumulate sufficient amount of data that can lead to building the model. Now, there is another way to do it, is by invoking artificial neural network or deep Q learning, which basically, each of this, network will represent some physical actions such as, discharge, voltage changes, gas flow, and such. And after significant training, without model, we can actually achieve, very similar results. So the one example of that is just on the plasma control, where say optical emission spectra can be used to identify just a few species from the large subset of say over 100 various species, and the AAN can be used to restore full chemical composition of the plasma, right? And that can lead to optimizing the condition for various applications. So say, we know some markers for cancer therapy, for wound healing or decontamination, and that can be multiplied by ANN, and to find what would be the right say temperature in the plasma to provide those conditions. In addition, we need to also worry about safety of such protocol, and recently some work was done also to develop what we call safe Q learning, where we utilize Gaussian process to basically to avoid risky results which off target significantly in course of optimization. Okay, so this is basically state of the art of such system, where key, of course, is real-time monitoring. And I show you a few examples. There are many more that we are working at the present time, and the full-scale system will be demonstrated very soon. Now, by doing some of this analysis, we came to a very interesting understanding of kind of general action of a plasma in the medical application. And that's due to the fact that it was noticeable over time that while there are some similarity, which what we call direct and indirect treatment, just to to tell you what it means, is that direct, when you have say cells or tissue and you treat it in the presence of whatever liquids or culture used, or you treat the culture and then apply culture to cells without any plasma, right? So that means basically there are accumulated chemical species in the cell culture or water for that matter that can be later applied. But what people notice for some time, while there are some similarities, but there is a significant difference. And we try to uncover why this difference coming from and what is this difference. And this is a very, very simple experiment that was performed. So one, what we call CAP, is called atmospheric plasma. It's direct treatment of a plasma, and we are looking here at the cell viability. Now, what we can do, we also can choose some proxy, say hydrogen peroxide, right? And without activation, it's not toxic. So we can choose very, very low concentrations that will not be toxic. Now, if we take cells in the presence of a media and treat, and then replace with a new media, we got that effect, which is basically no effect at all with a new media. But then what we can do is take cells with a media, treat with a plasma, and then remove the media, but put concentration of hydrogen peroxide that was not toxic, and suddenly it became toxic. As you can see, in fact, it actually can approach exactly result of a plasma when it's applied directly, right? Which basically suggests that there is a process we called, for the lack of better term, activation, or it's known as sensitization, that actually start as soon as 10 seconds, which is kind of direct treatment of a plasma before any chemical species are even formed. And this process actually, creates some state in cells that slow deactivate in about few hours. So that basically suggests that there is this window between, say, 10, 20 seconds and few hours, when now you basically synthesize cells to some chemicals, right? And that leads to, of course, different ways to do this analysis. So one of them is what we call physical treatment. So then where we separate any chemical, species altogether by creating the barrier. And there's a physical barrier, and yet we do see that we can affect with this, plasma cell. So this is kind of more two-dimensional map of viability, where we have large plates and different wells, and we can look of how these cells are affected, which is actually very important, because this may create non-localized treatment, which is very important for very many diseases. Now, this effect, in fact, is very sensitive to flow rate. Just holistically looking, we can see that there is a minimum of cell viability, or maximum of effect at some particular flow rate. That's number one. We also show that this is not chemical in nature. For example, we can use scavenger of reactive species, and we actually have exactly same effect. Now, that leads to actually different type of, applying plasma, which now confined in the tube, and we can obtain very, very similar regimes. And that can be used, say, to synthesize cells for chemotherapy, right? With the ultimate game to reduce toxicity. So this is a good example of it. So this application of just discharge tube, we're looking at the cell viability, say at 4 minutes, we don't see much effect. But now if we do the same and then afterwards add particular drug, we can see significant amplification of drug effect, which actually suggests that you can reduce amount of drug and get the same outcome. Right now, more so, if
Michael, you have 2 minutes left.
Right. So now, more so, just if you compare physical versus treatment, we can see that for different cell lines, actually, this different modality can play a more significant role. For example, red here is cancer cells, and the blue is normal cells. So chemicals actually not selective at all. Actually, it kills more normal cells. But if you do just the physical treatment, you reverse and make it quite selective. So just skipping the last result, I want to show that we perform multiple animal experiment where we applied this plasma jet in non-invasive way outside of the brain, or discharge tube. And this is very recent experiment of a patient-derived model. It's a patient-derived tumor that implanted of mice. It's kind of best proxy for real tumor. And you can see here results where green is actually combination of a chemo and the plasma that we had to sacrifice these mice because they still were alive. So that basically suggests that this can be strong path for translational application of this approach. And these are my conclusion, that I think the key point here is that there is a very unique opportunity here by utilizing low temperature plasma in medical application, and this is through the adaptive nature of the plasma. Of course, the key here is in situ diagnostics. And as a side effect of working on that, there was some discovery of these two modalities that can actually play significant role. And I would like to thank my lab and funds that helped to do this work. And thank you very much for your attention. Thank you. Happy to take any questions.
Thank you, Michael. That's a very nice talk. I think we have time for one question if anybody has one.
May I ask a question?
Sure, Asher.
I kind of understand how this may work on external cancers like skin cancer, but what do you do with things like lung cancer or other kinds of internal cancers?
Well, what I show here is actually brain tumor treatment, which is non-invasive, and this is a tumor that deep in the tissue, and there is a penetration level. Of course, for small animals, we're talking about maybe 5 millimeters or so, but really it can actually penetrate through the bone. I didn't show these results, but there are a few papers that we recently published to show that this effect actually penetrates through the bone.
So you say the plasma goes through the bone without damaging the regular cells, the normal cells?
Yeah, to some extent, to a large extent, I would say.
Thank you.
Okay, thank you, Michael. That was really very fascinating. So we really appreciate your talk. If you could just stop sharing.
Thank you very much.
Ask Eduardo to share his slides. And in the meantime, I'll introduce him. So Eduardo Ajido holds a chair of excellence as professor of aerospace engineering at Universidad Carlos III de Madrid. I hope I pronounced the university name right. He was a visiting scholar and Fulbright scholar at MIT's Space Propulsion Laboratory and Plasma Science and Fusion Center. He's the founder and director of EP2 Plasma and Space Propulsion Team, has supervised about 20 PhD theses, published over 80 journal articles and over 150 conference proceedings. His team is involved in multiple collaborative projects with space companies and other research groups under the European Commission Framework programs and the European Space Agency, as well as national agencies. And he's presenting today on the subject of modeling propulsion plasma physics. So without any further ado, Professor Ajido, please. Eduardo, we can't hear you right now.
Eduardo, you have to unmute.
Okay.
Yes, thank you.
Okay, thank you. I was saying thank you very much to the organization for this invitation. I'm going to talk about modeling in plasma propulsion. This is not as fascinating as the talk we have had by Michael, but I hope also it helps to the panel discussion we have later on plasma propulsion. Okay. So let me see how it works. This. Sorry, gonna move this. Okay, so now it works. Okay, so sorry for that. Let's see, as a context, the plasma propulsion has become a dominant technology nowadays for inner space propulsion because it's much lower cost and the higher emission flexibility. Examples are that the new plasma propulsion platforms for geo satellites that Airbus, TLS, and other satellite manufacturers are developing, or they are already flying. Okay, then also we have that mega constellation like OneWeb or Starlink are flying plasma thruster. And also for the NASA Gateway Lunar Orbiter, the propulsion module is based on plasma thrusters, the one you see here. There are different propulsion technologies, plasma propulsion technologies competing in this market. Leaving apart micropropulsion that has its own specific technologies, We have two classes of plasma thrusters. The one that we can call the mature technologies, where we have mainly the ion thruster and the Hall effect thruster, including the several variants. The ion thruster, in a way, has excellent performances. Could be say that is the best thruster, but at the end, it's too complex electrically and it's too expensive from the point of view of the satellite manufacturers. And we have the Hall effect thruster that is much simpler electrically. This means that it's cheaper. And also it's also more throttable, so it has also larger mixing flexibility. So nowadays Hall thrusters are dominating the plasma propelled spacecraft. Then we have alternative technologies within the context of European programs called also disruptive technologies, where there is a group of that we can call the electrode-less wave plasma thruster, where we have the helicon thruster, the CR thruster, also the Basmir. These are simpler electrically than the Hall thruster. They don't have neutralizer, they don't have electrodes. So this allows that they could have a longer lifetime, although this has not been demonstrated. They are more propellant friendly, but they have a low thrust efficiency. So there are those that can one day compete against the mature technologies. Then there are other alternatives like the magnetoplasma dynamic thruster, the plasma thruster, other exotic ones, okay? I'm going to concentrate my discussion on the Hall effect thruster and the EPTs. Well, then why modeling and what and how to model this type of electromagnetic thruster? Okay, modeling is aiming to understand the physics of the plasma discharge we have, and also to support the thruster optimization and qualification, all that can be called the thruster development. In the case of electrode-less plasma thruster, there is a need to assess whether they could substitute eventually the Hall thruster. They can be competitive in order to pursue with the development program. In the case of the Hall thruster, which they are flying successfully and commercially, why we need to, let's say, more modeling, okay? Well, there are several reasons. One of them is that the spacecraft market is very competitive. So small design improvements can provide large commercial benefits, okay? This can be an example of this in the transition from the unshielded Hall thruster to the magnetically shielded Hall thruster that I will comment later. But then we have that the plasma discharge physics are incompletely understood. So we cannot derive predictive simulation tools, okay, helping this thruster development. In fact, flight qualification in vacuum facilities of new thruster is very costly and it's a painful process. Indeed, this problem is more acute when we go to high power because there are few facilities for testing high power thruster. Indeed, there is now a new US initiative called Janus for high power testing. Okay? And then the qualification becomes more problematic also when we want to thruster for a multi-mission. We want to operate it with different operational conditions in terms of power, thrust, or a specific impulse. Then there is the issue that the operation in free space is not exactly like operation on ground in the vacuum facility, okay, where we have the background pressure and where we have also the electrical connection between the thruster and the facility. So attaining predictive simulator could speed up much the new developments of plasma thruster. If we go to what we need to modeling, what are the main challenges? We go to this type of thruster, we have several phenomena to take into account: ionization, the plasma heating, mainly electron heating, interaction of the plasma with the walls, the acceleration process, and then the expansion of the plume and the interaction with the spacecraft surfaces like solar panels. Okay. The main challenges lie here in the interaction of the plasma with the walls, and then there are also challenges in plasma heating and the plume expansion. Okay. The fact, as we can see in this plot, is that the plasma has a strong interaction with the walls. It goes to the walls. Okay, so walls are not walls in the plasma. We have that we have ion recombination, we have electron collection, etc. And indeed, in this thruster, plasma flows to the walls can amount to more than 20% of the total power. So this needs to be minimized. Behind these heat loads, we have the issue of wall sputtering that limits the thruster lifetime, in the case of the Hall thruster, for instance. So if you go to the plasma wall interaction, this is going to depend on the magnetic confinement, on the plasma condition near the wall, and on the properties of the material, of the wall material, of course. Indeed, new designs of Hall thruster trying to improve the magnetic confinement, but there are also pros and cons in this. This is a conventional annular Hall thruster where the magnetic field is mainly radial, and now we are moving in many new designs to this magnetically shielded thruster, where the magnetic field here is parallel to the walls, and this can reduce much the fluxes of plasma to the walls. And indeed, they claim that erosion is very low in this type of thruster. Okay, we have also what is called the Caspid field thruster, or the German HEMT, where they use this type of magnetic topologies with the magnetic field parallel to the walls, except in the cusps. And also it is claimed that erosion here decreases a lot. So this is good for in terms, these two solutions are good in terms of lifetime, but in terms of thrust efficiency, there is not much difference between these cases and this one. Possibly because the ionization process and the acceleration process are less optimized in these cases than in the conventional thruster. Okay. Well, anyway, if you want to go, if you have magnetic confinement, the problem that happens is that these magnetic fields lead to the emergence of several instabilities. Some of them produce turbulent transport, and this turbulent transport reduces the magnetic confinement. So we are in the kind of flow where we need a larger magnetic field to have an adequate magnetic confinement. But we are in a space, and the magnetic circuits, the magnetic system is very heavy. So we need to minimize the mass and therefore the strength of this magnetic circuit. So one way to mitigate this deconfinement by turbulent transport would be to try to control turbulence. But if you want to control turbulence, the first thing is that we need to understand how turbulent transport is. And this, in fact, is not well characterized yet. So, for instance, if we go to the case of the Hall thruster, the issue lies mainly in which is basically an asymmetric, axisymmetric thruster. The issue lies in the axial momentum equation, where we are having, this is the one that is going to determine the axial transport. And the only force that we have to compensate this one are collisions, but our problem is very weakly collisional, or other effects. And here is where turbulence appears. This turbulence force would come from azimuthal instabilities, or instabilities with large azimuthal component that have correlated behavior in the oscillation, such that we have a net force when we average on theta and on time also. The main candidates today in the community are thought to be the electron synchrotron drift instability, which is a kinetic one, of the drift gradient instabilities, okay, which is mainly a fluid one. This one is known in a very, I mean, it's characterized in very ideal homogeneous condition of the plasma, while our plasma are largely inhomogeneous, okay. These drift gradient instability are very natural to the large discharge gradients that are present in our simulation. We find experimentally and in simulation instabilities in the plasma with frequencies of wavelengths compatible with both of them. Okay, but this has not been yet fully characterized. We don't know very well how they depend on the plasma parameters. We don't know the amount of turbulent transport they give, etc. And then it also happens that since the discharge is highly inhomogeneous, that we can have different modes in different regions, okay? And that is the issue, or whether we can macroscopically define this turbulence force, okay? So then here we have example of these instabilities happening near the anodes, one of them happening in the near plume. Another issue we have is whether this turbulence force would be a smooth force or it would be oscillatory. We have some hints that it can also have an oscillatory behavior in the axial direction, which makes the problems more complicated and also makes that the electron inertia that is normally neglected can have an important role in this turbulent transport also, okay? And then an issue that has not been much assessed in the propulsion community is how turbulent transport affect the energy equation, the electron heat. Indeed, if we look to this component of the electric field work, most of the models today assume that this is zero, but this would be to be assessed. You go to the plasma wall interaction, to what happens near the walls. This is going to depend on the material properties. On the one side, we have the ceramics, presents a large secondary electron emission. This reduces the device sheet fall, and this at the end is going to modify the electron velocity distribution function near the wall. We have also an issue with determining the secondary emission and sputtering yields of ceramics. Okay, but this is from the point of view of the material. From the point of view of the plasma, we have that our velocity distribution function is non-Maxwellian. We have a partial deflection of the tail, high energy tail of electrons that have been collected by the wall. This has been found in this simulation, for instance. We have this deflection, and then we have two counter-streaming beams on secondary electrons, okay, that we can observe here. How are their distribution function? But are they staying within the plasma bulk? Are they being recollected? Which is going to be the history of these secondary beams. Okay, we have learned some lessons from a 1D kinetic model that have been developed in our group. One find that these are some of the findings. We find that the secondary emission is partially recollected. We find that the replenishment of this tail is much enhancing where the magnetic field is oblique to the wall compared to the case when it is perpendicular. There are larger radial asymmetries in the case of the annular geometry, and we are able from the kinetic solution to find consistent macroscopic laws, okay? So we are able to measure in the azimuthal electron equation or the energy equation, which is the contribution of the different terms, okay? For instance, we find that the pressure tensor is a full tensor where we have zero viscosity effects that at the end seems to explain the near wall conductivity that has been observed, but also they contribute to energy flux. And also we find that the heat flux in the direction parallel to B is non-conductive. It does not follow Fourier law. Instead, is proportional to the flux of enthalpy. Okay. Moving to the last example with the plume expansion physics, to the last challenge, we have that energetic plasma plumes can damage the spacecraft surfaces and the solar panels. Okay, the energy fluxes of this plume depends on the condition of the thruster exit, of the magnetization state of the plume. The case of an ion thruster where there's no magnetization is different from the case of electroless plasma thruster where we have magnetic nozzle, we have this type of magnetic lines, or the case of the Hall thruster where it's more complicated, the magnetic field topology in the plume. What we know from experimental evidence is that there is plume cooling, that the temperature of the plume decreases as we move downstream, and at the end, the potential fall in the plume is about 3-4 times the temperature at the axis of the thruster. Okay, but we don't know well why is this. Okay, the fact is that the plume is near collisionless, so the electron cooling has not, let's say, fluid collisional adiabatic nature, but is non-local and kinetic. Okay. Lesson that we have learned from models with paraxial magnetic nozzles, where we have a nozzle like this, we have a source of plasma here, and we look for the expansion with blast of models, is that the behavior in the conversion and diversion sites are quite different on the one side, then that the doublet population of electrons exists in the diversion site, electrons that are not connected to the upstream plasma, okay? And this indeed can dominate the plasma density in this region, but are difficult to assess because their nature come from either from transient effects or from the rare collision that we have, okay? This type
Eduardo, you have 2 minutes left.
Okay, I'm finishing. This is also reported in Lambert probe theory, we know that. Then another point that we find is that the magnetic mirror effects affect differently to ion and electrons. Indeed, it's seen stronger in ion than in electron. For instance, the conversion side, the electron distribution function remains Maxwellian. This is not the case with the ions. We're able to obtain also consistent macroscopic laws from the kinetic solution. And again, we find that the parallel heat flux is non-conductive, and we find again this same type of law that has also been reported in plasma fusion. Okay, and then when we need to distinguish between the individual magnetic mirror to one particle to the collective magnetic mirror to one population. And what we find for electrons, a bit surprisingly, is this collective effect is quite marginal. These terms is much smaller than the pressure gradients. Okay. And then to complete how must be this plasma modeling, we have seen for the examples I have shown you that electron models must be kinetic in order to start all these effects of turbulence, bloom cooling, etc. Okay, but this has a huge computational cost if we want to study thruster performances, because if we want to simulate a discharge, 1 millisecond of the discharge, that is the time we need for a steady-state recharge. We have this difference in time steps needed to simulate one of the other. So we need to move one neutral every 10,000 iterations of an electron typically. Okay, so if we want to have code simulator for applied research on thruster in order to study performances or the thruster plume facility system, we need to use fluid electron model where we have this, that the times for electron and ions are more or less similar. Okay. But can we have electron fluid models that can be derived consistently from kinetic model? Okay, we have had a good success with these 1D kinetic models. We are now dealing with full 2D case, but we expect that only approximate macroscopic laws, but that can be perhaps very useful, can be obtained. This is due to the non-local electron transport in the rarefied magnetized environment that we have in this type of thruster. That is all on my side. Thank you for your attention.
Eduardo, thanks for the nice talk. Unfortunately, we don't have time for questions, but I think you can send in the chat some questions for Eduardo or talk offline. But I'd like to thank you for your very nice talk. That was really very informative. And the next talk is also going to be on space propulsion using electric propulsion. So please, Eduardo, stop sharing. And Dan, can you share your screen?
Sure. I'll share it right now.
Okay. Dan will be presenting on heaterless cathode technology for plasma propulsion applications.
It says that the host is still disabling the screen sharing option.
Okay, I believe I made you co-host, but it didn't stick. Let me try again.
Oh.
Okay, try now.
Now it works. Perfect.
Great.
Okay. Okay, so I guess you can see my screen now. All good?
Yes.
Perfect. All right. So my name is Dan Leb, and I will be presenting a few things about the heaterless solid cathode technology, which is pretty much all the rage in the past few years when it comes to plasma propulsion. So I will just dive right in, and I'll explain the general background of what is plasma propulsion in general, why do we need a cathode, and what is so special about this type of cathodes that is working so nicely. So in general, plasma propulsion is a form of propulsion that enables us to maneuver satellites in space. So we can execute a whole different variety of applications that require any motion in space, and that can be geostationary space station keeping for a spacecraft, or just deep space missions, or satellite servicing if you want to fuel satellites, and so on and so on. So plasma propulsion gives us the ability to do so, to maneuver in space in a very fuel efficient manner. Now, the way it works is very simple. We just eject gas in one direction and we move the or propellant. We also call it propellant. And then we move the spacecraft in the other direction. So Newton's second law works very nice here, action and reaction. And the gist of electric propulsion is that it enables us to move or to shoot out the propellant at very, very high velocity, which means that we would need a lower mass of propellant in order to perform a certain maneuver. So it's very fuel efficient, right? Now, electric propulsion in general, the way it works is that we have propellant, which is stored on one end of the spacecraft in a propellant tank. It is ionized in different manners. There are different types of electric propulsion, but essentially most or all of the propellant is being ionized, and then it's being put through a set of electric fields that accelerate and shoot out that propellant out of the thruster and into the vacuum of space. Now, in general, the way it appears is we see plasma. It's very simple, right? So what we see in electric propulsion is just a bunch of ions, so ionized gas, and the light that we see obviously is being emitted by the collisions between the free electrons that collide with either the neutral or ionized gas. So this is what it looks like in general. And most of these devices that shoot out ions need somehow to neutralize those ions. Think of the ion, each one of the ions being ejected out of the thruster leaves the thruster or the entire spacecraft negatively charged. So each one of those ions that is being ejected has to be coupled or recombined with an electron in order to neutralize it. So this is what those cathodes do. They're basically electron guns. So they're first of all closing the electrical circuit. So they're the negative terminal of the electric thrusters. They're neutralizing the gas, the ions that are being ejected, and they also help in the initiation of the thruster just by providing the necessary primary electrons to start up the thruster. So this is what it looked like. You can see an internal cathode here, just a standalone cathode in the top right corner. They look like basically a cigar, which is a little bit wider. Now, common requirements for these cathodes for electric propulsion is they have to operate usually anywhere between 1 amp and 100 amps. There is one cathode that operates in the entire range, but most cathodes operate in the, I would say, 1 to 10 amps in that range. They have to operate for longer than 1,000 hours and more than 1,000 ignition cycles. So this is roughly the general requirements of these cathodes. At the end, every second in which the thruster is working, this cathode is ejecting electrons to neutralize the ions that are being ejected out of the thruster. Now, the general configuration of these cathodes is very simple. So looking at the right-hand side, what we see is something that's called a cathode insert or the emitter. Now, the emitter is just a low work function material that once it gets hot enough, it starts emitting a lot of electrons. And these are the seed electrons or the electrons that we use to cause the whole neutralization process. Now, before we even start the main discharge or the thruster itself, and you should focus a little bit on the left-hand side schematic here. What we usually do is we heat up that emitter just by starting a coil, usually, or just something that in general is called a heater, and that heater is being heated up to high enough temperatures in order to heat up the emitter, and then we can start the whole sequence of operating the cathode. Now, usually what we have is two-stage operation of the cathode after the emitter is hot enough. So once the whole thing is hot enough, electrons are being emitted. We start something that's called the keeper power supply. That keeper power supply ejects the electrons out. and then we can start the main power supply or the anode power supply, and then it takes the electrons and shoots them out of the cathode. Okay, so the general configuration of the cathode means that we have to inject the gas, start the heater, wait until the whole thing gets hot enough, start the keeper power supply, and then the main discharge. Now, heaters break, and that's the main problem with cathodes in general. Once you turn them on, you wait till the whole thing gets hot enough, turn them off, then turn them on again, and so on and so on, thousands of times. Essentially and eventually, that thing will break, and that's the main problem of cathodes. So the idea,
1 more minute.
no problem. So the general idea of heaterless cathodes is just to take that heater, get rid of it, and try to initiate a discharge inside the cathode in order to heat up the entire interior of that cathode. And that's the way to bring the emitter to the high enough temperatures necessary to emit the right electrons. Okay. Now, I will just go through a general scheme of the stages, and we'll conclude with that. But in order to do that, in order to replace the heater, what we need to do is we need to cause a plasma breakdown. That heating discharge has to be created somehow, which means that we will have to probably raise that voltage to high enough values and create a passion breakdown. So we'll have to do that as first stage. Second stage is we'll have to maintain a discharge which is hot enough to heat up the interior of the cathode as it heats up. So we're starting from a cold state. And then after the whole thing gets hot enough, it might take seconds or minutes. Then we can reach steady state operation conditions, and we can keep operating the cathode properly and supply the necessary electrons. Okay, so I'll conclude here because we don't have enough time. If you have more questions, you can ask me personally via email, and I'll give you more data. Thank you.
All right, thanks, Dan. Please stop sharing your screen.
Mm-hmm.
And yes, we don't have time for questions, unfortunately. So Omri, please share your screen. Omri will be presenting on optical emission spectroscopy measurements of the narrow channel Hall thruster plume. Omri, you can begin. And you're muted.
Thank you. Can you guys see the screen?
Yes.
All right, so let's get started. Today, I'm going to talk about optical emission spectroscopy measurements for the narrow channel Hall thruster. So I'll start with the need for low power electric propulsion, or EP in short. Today, nano satellites are becoming more popular for space missions due to their low launch cost. And they require a propulsion system to perform a variety of space missions, such as formation flying, etc. Ideally, we would like to use efficient EP devices for propulsion. The problem is that the power supply for nanosatellites is limited to usually below 30 watts. So there are only limited plasma propulsion solutions available for these power levels. Hall thruster are a very popular form of EP configurations. The problem is that performance drops dramatically with power below 100 watts, and there are no commercially available thrusters below 30 watts. So a new concept was developed at Technion called the narrow channel Hall thruster, or the NCHT in short. It has a unique design feature that allow its operation at very low power levels. We're talking about around 1 millinewton of thrust at about 20 watts of power. Here we can see the NCHT in operation. So in order to improve future design, we need to understand the governing physics of this new type Hall thruster, which can be quite different from the classical Hall thruster. In particular, we want to study the spatial variation of plasma parameters. The challenge is the very small geometry of the thruster. We're talking about a 30 millimeter channel diameter, and the annual channel is only 2 millimeters long and 1 millimeter wide at the exit. So really traditional measurement techniques such as electrostatic probes are not suitable inside the channel and in the near plume region here, because it's really a millimeter scale discharge. So our solution was to use a non-intrusive method for plasma diagnostics called optical emission spectroscopy, or OES in short. In OES, we observe the spontaneous light emitted from the plasma, and the idea is to deduce the plasma properties from the emitted spectra. The pros of using this method, it's very simple and less expensive experimental setup than, let's say, other laser-based method. And you can also track down multiple species at once. The downside of this method is it requires, it's harder to extract the useful data from the measurement because it requires a complicated theoretical model that links the emitted spectra and the excited level population. It's also hard to obtain the relevant cross-section database for those models. So to be more specific, when we measure a light intensity IPK for a transition from a higher energy level P to a lower energy level K, it's given by K, the calibration factor, times the NP, the excited level population of the upper level, times the relevant Einstein coefficient. So once we measure the light intensity of a specific line, we can get NP, the excited level population. But how do we go from the plasma properties to how do we go from this excited level population to the plasma properties? Well, that really depends on the plasma regime and the appropriate population model for this regime. Hall thruster plasmas are actually non-equilibrium, and that requires the most general description of the energy levels with a model called a collision or radiative model, or CRM in short. And in CRM, we take into account all the important contribution to excitation or de-excitation of the excited levels. So xenon in general has a very complex spectra with very limited cross-section database because it's such a heavy atom. And for many years, there was no available CRM for xenon. However, in 2006, Karabachak, Chiu, and Dressler developed a CRM for xenon called the KCD model. It was developed specifically for Hall thruster. It has simplified transition equations as well as the rate coefficient database. It was used for obtaining one-dimensional and two-dimensional electron temperature measurements in Hall thruster by various research groups. It's considered accurate between 1 to 20 eV with typical errors of 10 to 20%. It can be used for various gas densities. It considers all the processes in Hall thruster that leads to significant spectral emissions, such as electron impact excitation and ionization, and ion impact excitation. It relies on 8 near-infrared xenon 1 lines, or only some of them in the range of 780 nanometers to 980 nanometers. And the electron temperature is actually found from the best fit that minimizes this cost function, chi-square, which is basically sum over the square errors. So the model was implemented and validated. And after that, we could move forward to the experimental measurements. So this is our experimental setup. We have the narrow channel Hall thruster working inside a vacuum chamber, and we can observe the xenon plasma plume through a glass window. Here we have the long distance microscope, which we call LDM in short. It is placed over 2 identical linear stages that allow us pure translational motion along the axis of the thruster. And this LDM has 2 channels. One is connected to a CCD, which allowed us to align our optics and also determine the spatial resolution of our measurements. And the second channel is connected to ocean optics flame spectrometer, which has a pretty wide range, but a very low spectral resolution, about 1.5 nanometers. So after the experimental setup was assembled, we performed wavelength and relative intensity calibration with calibration lamps. And for the first time, took measurements of our xenon plasma plume. So here we can see typical spectroscopic measurements of the xenon plasma plume of the NCHT in operation. We could identify 7 out of the 8 near-infrared lines that are used in the KCD model. The only line we couldn't clearly identify was the 980 nanometers line because it couldn't be deferred from the background with good signal to noise ratio. So
Umar,
it
you
was
have 1 minute left.
Thank you. Really, it was omitted from the analysis, and we obtained the electron temperature from the optimization algorithm that I talked about from this kind of measurement, and we obtained a one-dimensional axial profile of the electron temperature. Here we can see the results for this first time near the exit plane. Here in the black dashed line is the exit plane. So for the first time, we could get results near the exit plane. Here in the green curve is the KCD model results. And we can see that the electrostatic probes can't get close to the exit plane. We compared the results to the electrostatic probes. And first of all, we used all the 7 lines that I talked about for the fitting. And as you can see here from the comparison of the light intensity, the optimization results weren't satisfying. More recent publications suggested that the KCD model overestimates the metastable population and suggested using only 3 lines that are not associated with the metastables for the fitting procedure. So when we did that using only the 3 lines, we got a better agreement, as you can see here from the line intensity as well. However, there's still only partial agreement because we would expect at some point the electron temperature will drop, and we didn't see that. We think maybe it's the alignment of the optics, or how do we estimate the line intensity, which due to the low resolution is from the peak value, and no real line function fitting was done. For future, we plan to estimate the errors, use a higher resolution spectrometer, take measurements further downstream, and also use a recently published Xenon CRM that showed great promise for Hall thruster diagnostics. That's it.
Thanks, Omer. Very nice talk. Again, no time for questions. Sorry, we're running tight, but now we're going to move on to a talk by Professor Amnon Fruchtman on plasma-based mass separation by waves and space charge fields. So Amnon, can you share your screen? Okay, I can see it. And if you could just enter full screen mode, perfect.
Okay, thank you. So good afternoon. My talk is about plasma-based mass separation by waves and space charge fields. These are examples for separation needs. Some of them are for isotopes, separating lithium, neon, or uranium. Some of them are for separating different materials. Important task is spent nuclear fuel. And there are various ways that people try to separate particles, and I will speak about mass separation by the ponderomotive force. The ponderomotive force is generated by combining the electric and magnetic field, usually of a wave. Here it's written the expression for this force, where B naught is an axial steady magnetic field, and E1 and B1 are the oscillating electric and magnetic field of the wave. Omega is, of course, the frequency of the wave, and omega naught is the cyclotron frequency of a particle in the steady magnetic field. So this is a non-linear force. It is a product of the electric and magnetic field, and as such, it is weaker than the usual force due to the electric field. However, near the resonance, this is the cyclotron resonance of the particles, it can be larger, and actually it can become a first order in the fields if you operate near the resonance. But more, what is very attractive about the ponderomotive force in certain conditions, the conditions are that it will be a standing wave, and with the right polarization. For ions, it should be left end polarized wave, is that the direction of the force is axial, but the direction of the axial force depends on the value of the frequency over the cyclotron frequency. And since the cyclotron frequency depends on the mass of the particle, particles of different mass, even small difference, are pushed in opposite direction. And this is, of course, very attractive for the use of mass separation, because what you can do is you can apply force on particles and push them in axially in opposite directions. So this is really attractive. The problem is that if you want a significant yield, one has to operate in a plasma. In a plasma, there are various problems, but one of them is what I left in red, is what is the effect of space charged fields. So plasma generates electrostatic fields that can jeopardize any effect of the waves. And my purpose in this very brief talk is to show that one can use the ponderomotive force in order to force the electrostatic force to operate in a favorable way. So just, this is a configuration. It's not built, it's just what I suggest for the configuration, is that you have your neutrals that you inject them from the sides, and here you launch, and there is a uniform magnetic field, and you launch a wave, a standing wave, in that direction, and the wave exerts force on the particles. Now, there are two kinds of particles. In green, this is the majority, and in red, this is the minority. You can think about neon 20, which is the majority, and neon 22, which is the minority that you want to separate. Now, you ionize somehow most of the plasma, but there are neutrals all the time. It's an ionizing plasma. And the plasma, because of the magnetic field, moves naturally in both sides. Without the wave, it just moves symmetrically to the right and to the left. And then you operate the ponderomotive force. And in this specific configuration, I exert the ponderomotive force only on the majority ions. Only the majority ions are resonant. And so the ions are pushed by the electromagnetic, by the ponderomotive force, and also by pressure, and they ionize, which also gives some momentum, or takes some momentum away. And what I thought is the fluid equations, in this case, that you have a force to the right, ponderomotive force to the right. Here is the neon, and is an example. So it turns out that there is one crucial parameter with a normalized ponderomotive force, which is the ponderomotive force over the mass of the particle, the acoustic velocity, the ion acoustic velocity, and the ionization frequency. And now I assume for simplicity that this force is uniform. And then I solve the fluid equations, the one-dimensional fluid equations along the magnetic field. So what you see is the results are for three values of these normalized ponderomotive force. When it is zero, it's the black. The flux of the majority ion is symmetrical. You get half to the right, half to the left. Once you increase the force, the flux to the right is larger than the flux to the left. And if you get this force nearly one, you get a large flux to the right for the majority and a small flux to the left. Here, these are solutions as a function of the Mach number, which is 1 or -1 in the two sides. Now, what happens is that because the particles are pushed to the right, I didn't show here, I do not show the density. And since the plasma is ionizing, the density of the plasma, the majority ions, and of the electrons becomes much larger to the right than to the left. And therefore, there is a pressure gradient by the electrons to the left. This pressure gradient on the electrons, they are in equilibrium, is balanced by the electric field. And therefore, the electric potential ceases being symmetrical, and a bias, but a positive potential is on the right. You see, when there is no force, the potential is the usual potential which is symmetrical and pushes both ions symmetrically to two sides. But as you increase the force, the potential, there is a potential build that is several times the electron temperature. Now, what happens to the minority, which we are looking for? The minority ions are non-resonant. Therefore, they are pushed mainly by the electric field. And in this potential, they are pushed to the left.
Amnon, you have 1 minute left.
Okay, so what you see here is that the flux of the minority ions, instead of being symmetrical, becomes larger to the right. So the end result is that by applying ponderomotive force on the majority ions, they push them in one side, a self-consistent space charge electrostatic field is built that push the minority ions to the left. And this way, we can actually make use of this space charge field that is considered to be a problem. So there are still difficulties. One has to think how to launch the correct wave. And actually one can think about the shear Alfvén wave or ion cyclotron wave, which are the exact waves which are appropriate for this. There is the problem of collisions. Now, collisions usually destroy the resonance. However, I think that this process is so efficient because you just collect the particles in both sides so that you can operate in a lower density so that collisions are less of a problem. I can mention that this is competitive to ICR, ion cyclotron resonance, which is developed in Curciato. And in Curciato, when they do it, is they hit the resonant ions, but then all the ions flow to the same direction. It's very difficult to separate them. So this gives an advantage that I think is worth exploring. Thank you.
Thank you, Amnon. Again, no time for questions, sorry. But Amnon, can you please stop sharing your screen? And next will be Professor Asher Yahalom, presenting on a three-function variational principle for stationary non-barotropic magnetohydrodynamics. Asher, can you share your screen, please? Asher. Okay. And please make sure you're unmuted. Excellent.
Okay. Good afternoon. A very brief talk about a free variational principle for stationary non-barotropic magnetohydrodynamics. Was done partially in Ariel, partially in Princeton. I would like to thank Professor Alan Raymond for suggesting many things concerning this work. There is a very long bibliography, but let me just point to this recent paper, in which all the details I will not give now can be found. And there's also the previous paper by Honkin and myself. Okay, just to describe the problem, MHD is about finding 8 functions: magnetic field, velocity field, density, and entropy. There are some derived quantities like current and pressure. And essentially, you have to solve a set of very ugly equations, which are partial derivative, nonlinear, and difficult to solve. This is an ideal MHD, so we are not discussing here conduction or heat generation. Entropy is just convective. The question is, can we do something to simplify those, and can we derive those from a variational principle? So let me briefly introduce some concept. A METAG. A METAG is just the flux. You take a magnetic line, you build a small tube around it. You look at the magnetic flux and you look at the mass inside this tube, and you divide one by the other. The mass is conserved, the magnetic line are co-moving, and therefore you get this load quantity, which is also conserved. And because it's built the way it's built, the gradient of lambda dot B is equal to null. Actually, you don't use those. You use the equi lambda surfaces to calculate a quantity called chi, which is just the magnetic flux going through these surfaces divided by 2 pi. It's also co-moving, so the material derivative is null, and it's made of magnetic field lines, so B dot grad chi is null also. And then there is another quantity which is the same as before, but now you don't go all the way. You just go to a certain point along the line, and you call it the magnetic METAG. And it has, if this point is co-moving, this quantity is also co-moving, and it has the property that if you take the gradient of this mu and you dot it with the magnetic field, you get the density. Of course, we need a third co-moving surface if it's three-dimensional. And in this case, there is another co-moving surface called eta. And you can show that you can write B as grad chi cross grad eta, and then div B equals 0 is satisfied automatically. Chi and eta were introduced by Euler first. They call Euler potential, used by Sakurai for magnetic field. Essentially, there are two surfaces whose intersection is just a magnetic field line. Mu, the magnetic METAG, was introduced by Lindenbell and myself in 2008. Okay, so rho is essentially Jacobian of chi, eta, and mu. And if you take into account that those are co-moving, you automatically have conservation of mass. Now, the thing is, we also have entropy as a co-moving surface. If the entropy is magnetic field lines are on entropy line, that's one case. If not, that's another case. And in the other case, you can just replace the mu by S, and you get this expression. Okay, so what do we have? We have the density as a Jacobian. We have B as a grad chi cross grad eta. This is Sakurai representation. And now we need the velocity. And now we take into account that the flow is stationary, meaning that we have a discontinuity equation without the temporal derivative. So essentially, V must solve those equations. Div rho V equals naught. Rotation of V cross B equal naught. And this, if chi is also stationary, V dot grad chi equals naught, meaning that V is orthogonal to grad chi. Now you do the calculation, and you can find it in the paper. I cannot do not have the time to repeat it here. You get this form. And essentially all the equations are now solved except the Euler equation, which also takes a stationary flow. This you get from a variational principle. You have an action, you have a Lagrangian density. It has this form. It has a kinetic term, internal energy term, and a magnetic field term. You need to use thermodynamical identities, which are given here. And essentially, a Lagrangian is now a function of those quantities, chi, eta, and mu. And you get this Lagrangian if you take the variational derivative after some manipulations, which I give here in a few slides. but it will be difficult for you to follow. So if you are interested, just look at the paper. You get eventually the form of the equations. These are the boundary terms, those are the equations. Omega is the curl of V, it's the vorticity. And if you use some vector analysis identities, lo and behold, you get the equations of motion. So this is a description of stationary magnetohydrodynamics in terms of just three functions. I'll give just one example. Suppose that the density is uniform. Suppose you have an helical stratified magnetic field, and it's confined in a cylinder with a radius A, and we assume that Z equals 0 and Z equal L are identified. So it's a topological torus. And now it's easy to see that the magnetic field line lies on cylindrical surfaces, and therefore you can calculate the flux through those surfaces. Those are just the load surfaces. You get this term, and it's easy to calculate chi, which is just a function of radius. And now if you take into account that grad chi cross grad eta is the magnetic field, you get an eta function, which is double multiple valued. It's a azimuthal angle, and Z is also considered cyclic in this model.
Asher, you have 1 minute left.
1 minute will be quite enough, I think. Now you can find a mu function. This is non-unique choice, but it's the simpler one. And from this you calculate the velocity, and the velocity is just azimuthal, going round and round. And if you plug this into the equation of motion, you get an expression for the pressure. And if you take the pressure to vanish on the radius A, you get this relatively simple expression. So this is a demonstration of how the system works. And I thank you for your time.
Okay, thank you, Asher. Again, no time for questions. So please stop sharing your screen. And next and last talk in the session will be Amir Weinberg from Ariel University, speaking on dogleg design for a mega electron volt ultra-fast electron diffraction beamline for the hybrid photo-emitted RF gun at Ariel University. Sorry, that's quite a title, but Amir, please share your screen.
Okay, just a minute.
Okay, looks good.
So hello everyone. I'm Amir Weinberg. I'm a PhD student in Ariel University in the Accelerator Lab. And I will be speaking about the dogleg design for an MEV ultra-fast electron diffraction beamline at our hybrid photo-emitted RF gun. So the contents of my presentation will be a short introduction about our hybrid photo injector and the terahertz FEL in Ariel University, some introduction about MEV-UED, my dogleg design, our dogleg design and results. So we have commissioned an RF gun, ME gun, in Ariel University in collaboration with UCLA. It is a compact photocathode gun, only 60 centimeters, with electron beam energies 3 to 6.5 MeV and pulse direction of a minimum 150 femtosecond, with pulse charge up to 300 picocoulomb. The electron gun, the accelerator, is supposed to drive a super radiant FEL in the terahertz regime using a 90 centimeter undulator. You can see it in the end. It will be super radiantly at 1 to 3 terahertz. So this is the first beamline. It should drive an FEL, free electron laser. And we would like to construct a second beamline with a mega electron volt ultra-fast electron diffraction. Now, so far, most electron diffraction systems are based on kilo electron volt DC sources with low energies. And the performance of the electron diffraction will be tremendously boosted using the MEV electron source. The relativistic suppression of space charge forces will allow generation of ultra-short beams. So most important is the spectral resolution of the MEV, which is the emittance of the beam, and the temporal resolution, which is the pulse duration of the beam of the electron gun. So we have designed a dogleg section, what is called a dogleg in the scientific jargon, for the second beam line. So this way we can kick the beam to the side and back, and build the MEV electron optics is with dipole magnets and two dipole magnets in yellow and higher order electron optics in the middle. It is a dispersionless system, and it's designed so to be achromatic and okay. And the theoretical calculations for the dogleg was performed using the transport matrix R and the second order matrix T. The transport matrix is actually the combination of the elements. Each element, the dipole quadruples combined together. And we used the eta x, eta tag x, and eta zx in this way, that the eta x and eta tag x we equal to 0. That's the transverse dispersion elements. And this way we calculated the magnetic fields of the quadruples. Also, the second order matrix was solved in a recursive manner in MATLAB. We can see here the second order optics numerical and analytical calculations. We compared them and we reached the same results, where the dispersion element T566 was diminished using a sextuple magnetic field of minus 14.5 Tesla per meter squared. The simulation for the dogleg was performed. There are several simulations of the entire RF gun and the beam lines, and we performed optimizations on the dogleg. You can see the bunch width, the bunch duration, and a positive chirp at the beginning of the dogleg, and a negative chirp at the end, and the waist at our sweet spot, that is 5 meters for the cathode of the gun, 1 meter from the dogleg, that is the vacuum sample chamber where the experiments will be held. Now, in order to receive a positive chirp at the beginning, we have to change the phase at the RF gun between the sections. That's a change of temperature, and the energy of the gun will be higher. So, because usually for the default for the FEL, the electron gun gives a positive chirp, and a negative chirp, and for the dogleg we get a positive chirp because it's a bunch compression. So the design optimization results at 5 meters from the RF gun cathode. for 30 picocoulomb, a normalized emittance of 1.45 micrometer, and a bunch length of 37 micrometer. For comparison, that's a 1.7 emittance, 1.7 micrometer emittance, and a pulse duration of 900 femtoseconds with the positive chirp.
Amir, you have 1 minute left.
Okay. So that is much better parameters for the NEV-UAD using our optimization process that we performed. Okay, so over here you can see a sketch drawing of the electron gun and the first beam and the dogleg section with the vacuum sample chamber. We used a renovated vacuum sample chamber. We renovated the vacuum sample chamber for our experiments with 16 ports and 6 ion pumps, and it reached a vacuum of 10 to the -9 torr. Okay, that is all. Thank you. We have some references here.
Okay, thank you, Amir. So it's now 3 o'clock Israel time, and it's time to start the roundtable discussion. So I'll pass the chair over to Igor Kronhaus, who will moderate.
Thank you, Joe, and thank you for audience here for staying to this last basically discussion of our plasma panel and plasma session. And we have very distinguished guests here. So I would like to please our guests. So we have Professor Eduardo Ahedo here.
Hi.
Can you open your, oh, excellent, we see you. I ask all the others, please turn off your cameras so we can have, we'll see our panelists and be easier, I think, to distinguish who's talking. Eduardo is the Chair of Excellence as a Professor of Aerospace Engineering in the Universidad Carlos III de Madrid. We have with us Professor Michael Kedar. Professor Michael Kedar is A. James Clark Professor of Engineering at George Washington University. He's also, by the way, the president of the Electric Rocket Propulsion Society, which is actually our topic here. We have also with us Amnon Fuchtman, Professor Amnon Fuchtman from Holon Institute of Technology in Israel. And also participating is Dr. Dan Lev, which is also has more than a decade worked on electric propulsion in Rafael, which is a big government defense contractor, also on electric propulsion. So basically our panelists presented there are some of the work, but here we're focusing on specifically on space plasma propulsion and its current state and its future, bright future. So just to say a few words about myself as well. I'm an entrepreneur in space plasma propulsion. As I was active at the Technion until recently. And my name is Igor Kronhaus, by the way. We basically dedicate this session to electric propulsion in space. This is one of the examples, I think, leading examples of the use of plasma technology and very beneficial implementations that for all humanity. We have thousands of satellites in space currently flying with plasma engines, and we see only greater and greater need for these kind of devices. We have new challenges, and I would like our panelists to discuss these challenges as well. We're talking about small satellites, large satellites, even orbiting stations. So all of them, deep space missions, they require more capability from the current technology. So let's start. So I would first like to have some sort of assessment of the current state of successes actually in plasma technology related to to these plasma thrusters. So I'll ask Eduardo to start, and then if time is allowed, we'll continue like this.
Okay, thank you, Igal. I addressed this point at the beginning of my presentation before, indeed, about these recent successes. I think that the central one is this, that plasma propulsion has become the dominant technology nowadays for inner space propulsion. Today, more than 50% of satellites are implementing plasma propulsion or electric propulsion instead of chemical propulsion. This change has happened very quick in 10 years, more or less, or 10, 15 years. So I think that this is a major success of electric propulsion. At the same time, we are having several technologies that we are using. It's not a single one. We have several ones, some of them more appropriate to low power, others to high power, okay? Then I also to point out that plasma propulsion has been seen as low power propulsion before because of the onboard electric power was quite limited, okay? But this has also changed in the last 20 years. So now we have we can install a large amount of electric power with solar panel. We can install several hundreds of kilowatts in a space with flexible solar panels, and I think this has increased much the perspective for plasma propulsion, including the exploration of the moon, for instance. Okay, we have there, and I think that in the future also the exploration of Mars will be based on plasma propulsion. So this would be my contribution.
Thank you, Eduardo. Yeah. So anything else would you like to contribute? Maybe Michael, or maybe you can say a few words.
Yeah. Okay. Thanks. So I probably would just add from a little bit different aspect, and that's on can maybe miniaturization of electric thrusters. Yeah. So this is another big area, and maybe about 5 years ago there's a lot of voices that there is not much electric thrusters that can operate in this arena, say for for small cube satellites and such, and this field also exploded recently. And you can you can notice by just just a workshop that a couple workshops that were on the micro propulsion, kind of very dedicated, but also my micro propulsion section on IEPC, which is a major conference. There's a lot of different ideas, different thrusters developed, but the challenge still exists that all the systems are not necessarily scaling very well at low power, so you're losing a lot of efficiency. So there's quite a bit of work in that area. And what's also noticeable is that in electric propulsion there is a lot of industry, and in particular startups. I guess Igal probably will speak to that to extent, but we can witness a lot of startup in US and in Europe and other places of the world in this field. And maybe I will use that as opportunities just to tell the audience, not so many people actively working in this field, but we just started a new journal of electric propulsion. So this is will be a platform for really kind of unifying and bringing this together. This is by Springer, and you can find this information, I guess, if you look at it. Thank you.
Thank you, Michael. Dan, would you like to say someone from the industry itself, like the big industry, at least, not startup?
Sure. So I think that one of the main things that happened in the past decade is that the physics was already known to most extent when it comes to electric propulsion. It was just maturing it and bringing it up in the TRL, technology readiness level ladder, to make it more and more qualified to fly in space. So this is what companies did in the past decade. They took existing technologies and they basically made them feasible to fly in space. Okay, so there's a whole string of processes that you have to go through in order to be ready to fly in space. This is one thing. Another thing that a picture is worth 1,000 words. So if I can share, I want to show you one figure.
One figure. Okay.
Okay, there you go. So what you see here is the number of spacecraft using electric propulsion in the past 40 years, excuse me. So this figure here, I think you see this figure, shows the number of spacecraft. Now you see in the past 3 years, the green bars actually shoot up. They go way beyond 60. And what you see here is that initially in the past 30 years, 40 years, more and more electric propulsion devices were used for geo satellites, which are big, hefty 5-ton satellites working 36,000 kilometers above the Earth. Now, we look at the past 3 years, and we have roughly 1,000. Actually, this year we already crossed the 1,000 spacecraft with electric propulsion. Almost everything for small satellites, which means power in the range of 200 watts. Okay, and this says everything about the situation that we're at right now.
Okay, so that's the current situation. So I would like to ask, okay, what is the prediction for the future? Do you see, for example, and what are the applications currently? We said geosynchronous satellites are large telecommunication satellites, right? We said LEO, small satellites. What about also air breathing systems, for example? Maybe Amnon, can you say some words about that? The air breathing?
Yeah, I wanted to mention technologies that are interesting. I'm not sure if they will be successful, but they have a lot of interesting physics. So we, at least in the academia, are tempted to explore them further. And two topics. One of them is, well, electrodless, which I will speak in a minute because Eduardo already described them. But air breathing is a response to a need for very low electric propulsion that seems very difficult to accomplish. But I think that it's there is some improvement in this field that may make it possible. Air breathing, as you know, you want to use the propellant that is available at, let's say, a 200-kilometer latitude. And the lower you go, the drag is higher, but then the propellant is more available. And the question is, what will win? What will be larger, the larger drag or the larger propellant amounts that you can extract? Also, the propellant there is free. You don't have to take it with you in the air, but then you get what you pay for. You don't get a nice noble gas, you get nitrogen. You have a lot of energy going into this dissociation, and there are many propellants that one has to explore if they are feasible. But I think that it's very interesting to go and to search to explore this further, especially that some technologies are really making some associated questions possible, like extracting the air with less reflections. And so when this becomes more efficient, maybe air breathing will be really practical.
Okay. And what are the other technology you see?
And what?
What is the other technology you mentioned?
The other technologies that I would like to mention is all these electrodless that Eduardo mentioned. So these are divided into several things. One of them is just using waves or oscillating fields in order to ionize and increase the temperature of the plasma. And then the plasma pressure gives you the thrust. And one can increase the thrust also by having a magnetic nozzle. And so this is a field that theorists and experimentalists explored a lot, and it's very, there is a lot of greater understanding now that there was 10 years ago. So this is one question. What will be the potential heal that you can generate by playing with the magnetic field and specific waves? The waves could be either helicon waves or ECR. And what they do is basically putting energy in the electrons and then raising the potential, generating a potential which is several times the electron temperature. And this is what gives the thrust by accelerating ions.
Thank you. I think it's a very comprehensive answer what you tell us. So basically, we're talking about challenges in plasma physics to develop this kind of electrode-less systems. So maybe I'll segue to Eduardo. So what kind of techniques do you think? Do you think computer simulations, or what do we need in order to explore these alternative systems? Do you think it will be possible to develop better systems than the current classical ones, the whole thruster, the ion thruster? What are the prospects?
Continue to the point that Anand was discussing, and I want to add a comment, is that everything pertains to a family of thruster of technology where we want to use in situ propellants. Okay, we have saying that not to fly with all the propellant we need, but to take the propellant from where we are. Okay, and this is a very important idea if we go also into exploration. Okay, and in this field, these electron-less plasma thrusters are interesting in the sense that they are simpler systems. They don't need hollow cathodes. I'm sorry for that, okay, because they are not going to use the hollow cathode, but they are much more, say, propellant friendly. Okay, they can manage better different propellants. And going to your question, in this type of thruster, the main challenges come from first to understanding well the plasma wave processes and the plasma wave heating. Okay, this is not well enough understood. Okay, there have been progresses, but I mean, I have been involved in several of these studies, and none also, and I think that some aspects are not clear. And then the issue of turbulence, of the issue of turbulent transport. My personal opinion is that the low efficiency of this electroless thruster comes mainly because we have a large turbulent transport. Okay, that means large losses at the plasma walls, and perhaps these instabilities creating the turbulence are also enhanced by the plasma wave processes. So this is, I think, a large physical challenge. Okay, to study both things separately and combined.
Okay, thank you, Eduardo, for this very interesting comment. Maybe I will finish with Michael. I wanted to ask you about facilities, or what kind of instruments do you think will be required, or do we need? You said small spacecraft, so maybe small spacecraft are easier to test, like small engines, low power. So maybe, what do you think about that? I mean, we have this explosion of startups. What do you think about the easy or the how approachable these technologies could be?
Well, yeah, I mean, actually, I want to speak about something else, and I think
okay.
Eduardo mentioned. No. What I mean is that Eduardo kind of touched this in his talk during introduction, that on a larger power scale spectrum, there is a much more challenging problem on testing these thrusters. And we're talking about, say, hundreds kilowatts and more.
Right.
There's a lot of programmatic issues with that, and there are many ideas that can be explored, but facility just simply doesn't exist, to do those qualifications, right? And it started, as far as concerned with maybe even 10 kilowatt, where was kind of anecdotic experience in Aerojet corporations that created thruster, tested, and put it in space, and it was under predicting. So this is how this whole idea appeared. But in addition to that, the live testing, right? So say you're interested for maybe tens of thousands of hours of operation, and then how you do it on the ground, right? Can you have a modeling that will be predictive enough to assess lifetime of those devices? So this is on higher power, spectrum. It's much more challenging that it appears, and challenge not necessarily on understanding physics, but it's challenging on the facility level.
Right. So the technical side, right, and the huge programs. I would also mention air breathing here. It's also a challenge how you simulate this kind of environment. So this is it's big science basically becomes. So thank you. I think we are running out of time here. So I would like to thank our panelists here. Wonderful discussion, and very appreciative of you joining. So is there any question from the audience? Maybe it could be other topics to our panelists. So maybe you can just jump in if you like.
So maybe I'll ask a question. As many of you saw, Igal and I have been working together. Hopefully we'll continue to work together. And I've been doing just a little bit of optical emission spectroscopy on the plasmas for the small scale thrusters. I'm wondering what types of diagnostics maybe could be explored that would help in quantifying some of the unknown effects, maybe for the turbulence that Eduardo was mentioning. Is there anything that is needed that's not available?
The turbulence, I suggest you to use some kind of sharing imaging. In such case, you will be able to obtain turbulences in your fluxes. If you are talking about visible spectrometry, because we are talking here, even it will be pulse thrusters, still it will be not a nanosecond time scale. So microseconds or tens of microsecond pulses where plasma is visible, just common spectroscopy will be fine. And the problem will be only how to interpret data, because it's not always stationary plasma. And if it is transient plasma, it could be difficult to interpret it in density and temperature.
Right. So this is exactly the current problem of Omri. So yeah, thank you, Jakob. By the way, we have Jakob Prasik. Okay, so I think we can spare a few minutes more. I think we're already in the break.
Actually, if I can add, I know that the one group at JPL is actually doing time resolved optical emission spectroscopy, so it's already done and going. Yeah, it's definitely exciting.
We are doing this time resolved and space resolved spectroscopy, not only in Weizmann Institute, but also in Technion for already more than 20 years.
Yeah, but I was talking specifically about Hall thrusters. Yeah.
Hall thruster don't know. We also did this.
Yeah, go. Okay, you can talk to each other. I mean, you're nearby. Okay, so is there any?
I would like to add that we need to study not only the plume. We need to study also what happens with the plasma inside the thruster. Okay?
Inside, right.
And this is much more difficult. Okay, to have diagnostics that can go inside the thruster and to know what is going on there. Okay, because the issue of magnetic confinement is happening inside. Okay. And before, in one of the presentations by Omri, we have seen these nice temperature profiles, but they end at the exit of the thruster. No? Okay, So we will need to go inside also.
Inside, it could be only one way to do very clever doping, which will not disturb plasma. It could
Go
be
ahead.
done,
Yeah,
but
go
very
ahead.
carefully.
Okay, it challenges. Thank you for bringing this. These are
It's an interesting challenge.
very
Yeah.
interesting challenges. How you do this? We
We
were
did
hoping
this
to
in plasma
couple.
opening
Yeah.
switch. In plasma opening switch, we did this.
Yeah.
Yeah.
Okay. Okay. We'll have to look into it. But I was hoping to combine here experimental and maybe modeling to complete the picture, and I raise it as a challenge because we see this is a challenge. Simulation do not correspond to experiments and vice versa. So there's a lot of work there.
Well,
Okay.
Igor, one new technique that can be used with is also the data analysis techniques, sort about machine learning, etc. To try to characterize better all the data and the stabilities that are happening there. No, so this is
Right.
also another way to attack the problem.
Yeah, I haven't seen a lot of work using AI. But definitely, it seems like the rest of the world is doing it. I don't know, different applications. Why not into our applications? Okay.
Well, there is an effort on
is an effort?
that, you know, to predicting the transport of electrons, right? But we're talking about a little bit different. So we're talking about utilizing this in the diagnostics. That are also possible, and you know, as you said, it is done in other areas. So should be adapted.
We should adopt it as well. Right. Okay. So thank you very much, and I hope this was just a titillating kind of introductory to the interesting, I think, subject of space propulsion, plasma propulsion, and the challenges we have, and the great industrial interest as well, and the importance we see here. Okay. So thank you for the panelists and the audience. So bye for now.
Bye.
Thanks. Bye.
Yes, everybody, we have a few minutes of coffee break, and then the session's over, so you can return to the main
coffee break?
session for the plenary talks.
Where is the coffee?
I'll email it to you, Yakov.
The coffee is on
No
you,
need,
Jacob.
you can
The
drink
coffee
some
is on you.
virtual
You have to print it somehow to us.
The virtual coffee.
Bye.
Bye.
Right.